Alternating currents, class 5. In this class, I have discussed alternating EMF applied to series LCR circuit. And in this topic, I have discussed basic introduction, phasor diagram, expression for impedance, variation of impedance and current with frequency, phase difference between voltage and current, and finally, resonance and resonant frequency.
Hello students, good morning to all and welcome in my class. In previous classes related to this chapter, we have discussed so many topics. Our chapter is running as alternating current. In previous classes, we have discussed RMS value of current, peak value of current, average value of current for full cycle and half cycle. We have also discussed how resistor, inductor and capacitor behave with AC. We have discussed the concept of reactance, capacitive reactance as well as inductive reactance. But in this topic, we are going to discuss, in today's topic or in this class, we are going to discuss series LCR circuit. What is meant by this? Here, an inductor, capacitor and resistor all are connected in series, and we have to find out what will be their effective impedance and finally what will be the current flowing in the circuit. So let us suppose an inductor of inductance L. This is inductor of inductance L, resistor of resistance R, and capacitor of capacitance C. Capacitor of capacitance C all are connected in series with an alternating source of EMF. Inductor of inductance L, resistor of resistance R, capacitor of capacitance C all are connected in series with an alternating source of EMF V equals to V naught sin omega t. V equals to V naught sin omega t. I think you all might be knowing that this V naught is the peak value of voltage, omega is the angular frequency, and this V is the instantaneous value of alternating EMF. V is the instantaneous value of alternating EMF. Now, from previous classes, we know that inductor, resistor and capacitor, they are having different phase difference with voltage and current. For example, if we talk about resistor, in the case of resistor, voltage and current both are in same phase. I am representing like this, that we have discussed already. Okay, let us suppose this is the direction of current. This is the direction of current. Then in the case of resistor, voltage will be also in this direction, and that we can represent by VR. Voltage will be also in this direction. In the case of resistor, current and voltage both are in same phase. Current and voltage both are in same phase. But in the case of capacitor, current leads the EMF. In the case of capacitor, current leads the EMF by how much angle? Pi by 2. Therefore, we can represent the phasor diagram like this. This is current, and here it will be VC, voltage across capacitor. And now you can easily understand this angle is pi by 2, and the current is ahead of voltage by pi. We are measuring the angle as anti-clockwise direction. So here it is VC, here it will be R. And for the case of inductor, we know that phase difference is again pi by 2, but in the case of inductor, current is lagging behind the EMF by pi by 2. Current lag behind the EMF by pi by 2. Therefore, this we can represent the phasor for VL, and this will be the phasor for current. This will be the phasor for current, and therefore this angle is phi. So these are the phasor of N, R and C separately, but in this topic we have to draw a combined phasor diagram for this series LCR circuit, and finally we will find the impedance and current of the circuit. So just we have seen that in the case of inductor, resistor and capacitor, there is different phase difference. If we have to write the value of voltage, then we can write for an inductor. For an inductor, we can write VL equals to I naught XL. We know that the effective opposition offered by the inductor is inductive reactance. Therefore, VL can be written as V naught I. VL will be equals to I naught XL. Similarly, VC we can write I naught XC, and VR we can write I naught R. These are the values of VL, VC and VR, but we cannot directly add them. We cannot directly add them because they are the phasors and they are having different direction. Therefore, we will make a combined phasor diagram for series LCR circuit, keeping in view that here phi is 0, here phi is pi by 2, here again phi is pi by 2, and we will make the phasor diagram for series LCR. So I am drawing here combined phasor diagram for series LCR. And by using that phasor diagram, we will be able to find the impedance or effective opposition of series LCR circuit. On this side, we are taking current. On this side, we are taking current. Therefore, this phasor will be VR. VR because in the case of resistor, voltage and current are in sync. Since in the case of inductor, current lag behind the EMF by pi by 2. Therefore, on this side we have to consider VL. And in the case of capacitor, current is ahead of voltage by pi by 2. Therefore, if current is here, we have to take voltage across capacitor on this side. So let us suppose this I am representing VC, and here we are representing VL, and here we have assumed that VL greater than VC. It is arbitrary chosen. VL may be equals to VC, VL may be less than VC, VL may be greater than VC. Here I am considering VL greater than VC so that the combined phasor diagram will be in this point. If we consider VC greater than VL, then combined phasor diagram will be in this quadrant, and other there will be no effect. So since here it is VL, this is VC and this is VR, these three phasors we can consider as three vectors. Since these two vectors are oppositely directed, therefore the resultant of these two vectors we can write here, and that we have to represent by VL minus VC, because these two vectors are oppositely directed, and we know that whenever two vectors are oppositely directed, their resultant will be the difference of these two. That's why it is VL minus. Now we are having only two vectors. One is VL minus VC, other is VR. By using parallelogram law of vector addition, we can find their resultant. So let us suppose here I am denoting this. This is parallelogram, and therefore the resultant will be represented by this phasor, or that we can say as V naught. This is V naught. Here it is VL minus VC, this is VR, and this is V naught. And let us suppose this V naught is making an angle phi. This V naught is making an angle phi. V naught is making an angle phi with the direction of current. Therefore, if we have to write the phase difference between voltage and current, then it will be V naught into V naught into I. So V naught. Okay. So this is the phase difference between voltage and current. Okay. This point we have already marked O. Let us suppose this point is A, and this point we can mark as B, and this point we can also mark as. This is the point only here, O, A, B, C. So this is the combined phasor diagram for series LCR circuit. And now by using this combined phasor diagram, we will be able to find out the effective impedance of the. Now I think this up to this point it is very clear. These are the values of VL, VC, VR. Here we have taken current. Now, if we see this phasor diagram, it is very clear that OA, this is again vector, OB is also vector. Therefore, we can say OC. We can say OC will be equals to OA plus OB. This OC can be written as OA plus OB, but here we are interested in the magnitude only. Therefore, we can write OC equals to root over OA square plus OB square. Root over OA square plus OB square. Now OC, this OC we can write as V naught. This we can write as V naught equals to. Here we have to put the value of OA, and that is VR. Therefore, VR square plus this OB. OB is the resultant of VL and VC, and therefore OB can be written as VL minus VC. Therefore, it will be VL minus VC whole square. So by this phasor diagram, we can write this V naught equals to VR square plus VL minus VC whole square. And now we have to put the value of VR, VL, VC in this equation, and then we can solve. Clear? Now I am doing this diagram. So if we put the values of VL, VR and VC, then we can write V naught equals to VR. Just we have written that VR equals to I naught plus VL minus VC. VL is I naught XL, where XL is inductive reactance, minus I naught XC whole square. And now I naught can be taken out. Here it is I naught square. From this term we can also take I naught square. Therefore, finally I naught square will be taken out by the, and therefore we can write I naught. This will be only I naught, and here we get I square plus XL minus XC whole square. I naught R square plus XL minus XC whole square. And finally we can write I naught equals to V naught by square root over R square plus XL minus XC. This is the value of I naught, V naught by this. Now if we use Ohm's law directly, then we can say that I naught equals to potential difference divided by resistance, or we can say potential difference divided by opposition. This opposition is denoted by Z. Therefore, we can say as V naught by Z, because the dimension of this whole quantity will be of resistance we have denoted this quantity by Z, and it is known as impedance. Just we are going to define impedance. V naught by R square minus XC whole square equals to V naught by Z, where Z equals to this, and this quantity will have the dimension of resistance, and it is known as effective impedance of the circuit. Here Z equals to R square plus XL minus XC whole square, or we can also write as R square plus omega L minus 1 upon omega C whole square. R square plus omega L minus 1 upon omega C whole square. This quantity have dimensions of resistance. The unit of this quantity will be ohm, and this is known as impedance of the circuit. Impedance of circuit, and how we can define it? Effective opposition offered by the series combination of R, L and C is known as impedance. Effective opposition offered by the series combination of inductor, capacitor and resistor is commonly known as impedance, and its unit will be. Now from this expression, it is very clear that the impedance of series LCR circuit is not constant. Impedance of series LCR circuit is not constant. It depends on frequency. Therefore, as frequency changes, impedance will change. And if impedance changes, current going through the circuit will also change. Therefore, now we are going to discuss how the impedance of circuit varies with frequency, and finally current varies with frequency. So now we are discussing the variation of impedance with frequency. This is the effective impedance of series LCR circuit. In this topic, this is our main aim, to find out impedance of this series LCR circuit. This we can write as Z equals to this. We can also write like this. Now we are discussing the variation of impedance with frequency. So from this expression, it is clear that as we increase omega, this factor will increase, but this factor will decrease. And as we decrease omega, this factor will decrease and this factor will increase. Therefore, if we draw the variation of Z will be like this. If we draw the variation of impedance, the variation will be like this. On this axis, we are taking this is Z, that is impedance of series LCR circuit. Here we are defining omega, that is angular frequency. Omega is the angular frequency. So if we draw the variation, it is very clear from this graph. If we put the different values, then we will get this type of graph. Initially, Z decreases with increase in frequency, but it does not become zero because R is there. R cannot be zero. R will still remain there. Therefore, Z minimum will not be equals to R. This is the value of Z minimum. This is the value of Z minimum. This is the value of Z minimum, and it will be equals to R. Z minimum will be equals to R, and it will be only at a particular frequency. It can happen only at a particular frequency, and that frequency is known as resonance frequency. This concept we are just going to discuss, and this is denoted by omega naught. Resonant angular frequency, this we can represent by omega naught. Then from this diagram, it is very clear that impedance decreases initially, it becomes minimum, and finally it again starts increasing. This is the variation of impedance Z with, and now we can draw the variation of current. The variation of current will be just opposite. This will be the maximum value of current. Here we can say I maximum, this is, and here it is omega. And this frequency, the frequency at which current become maximum, that is known as resonant frequency. So from this variation, it is very clear that as we increase frequency, Z will decrease, it will become minimum at a particular point, and finally it again starts increasing, and consequently the graph of current will be like this. Initially current will increase, Z decrease, and therefore current will increase. Here Z become minimum, therefore current become maximum, and again Z increases, therefore current decreases. Now we are considering only this situation. Let us suppose we consider or we focus on this situation only. At this point, impedance is minimum, therefore current is maximum. This situation is known as resonance. The frequency at which impedance of the circuit become minimum and current through the circuit become maximum is known as resonant frequency or resonant angular frequency, and this phenomena is known as resonance. Here current will be maximum and impedance will be minimum. This phenomena is known as resonance. This phenomena is known as resonance, and it can occur only at a particular frequency. That's why we have to calculate that particular frequency. So we are writing here for resonance condition. For resonance condition, XL should be equals to XC, so that Z will be equals to Z minimum or equals to R, or I will be maximum. So for resonance condition, XL should be equals to XC, and therefore we can say that, let us suppose it is occurring at a particular frequency, and we are denoting by that frequency as omega naught, or we can also say omega, resonant angular frequency. So we know that XL equals to omega L, therefore it can be written as omega naught L equals to 1 upon omega naught, or we can say omega naught square equals to 1 upon LC, or then applies omega naught equals to 1 by root LC. Omega naught equals to 1 by root LC. This is known as resonant angular frequency. Resonant angular frequency. And if we have to write resonant frequency, then we know that omega is 2 pi nu. Omega is 2 pi nu. Therefore, we can write 2 pi nu naught equals to 1 by root LC, or then applies nu naught equals to 1 upon 2 pi. This is known as resonant frequency, and this is known as resonant angular. So this is what about combination of inductor, resistor and capacitor in series. This is known as series LCR circuit. In this topic, we have discussed what is impedance of series LCR circuit, and the answer of impedance is Z equals to root over R square plus XL minus XC whole square. Then we have calculated resonant angular frequency and finally resonant frequency. And now from the phasor diagram we can write last topic of this series LCR circuit, that is phase difference, that you can see from the diagram, phase difference between voltage and current. Here phase difference we can write from the phasor diagram that we have already drawn here. If we draw or if we see that phasor diagram, then tan phi can be written as, here we are writing tan phi, therefore it can be written as AC by OA, or AC can be written as OB. You can see the diagram is already there. AC equals to OB and OA. Now OB is VL minus VC, that you can see from the diagram, and OA is VR. Therefore tan phi equals to VL minus VC upon VR, or that we can also write I naught XL minus I naught XC upon I naught R, and this I naught will be cancelled out. Therefore tan phi we can write XL minus XC upon R, or phi can be written as tan inverse XL minus XC upon. So this is the series LCR circuit. In this circuit we have calculated impedance of the circuit, we have calculated resonant angular frequency, what is meant by resonance, how current vary with frequency, how impedance vary with frequency, and finally what is phase difference between